Alright, let's try to answer this example. So we have for a compacted soil, specific gravity equal to 2.72, water content 18%, or moisture content, and the dry density is equal to zero point 0.9 of the a zero air void density. Now determine the unit weight of the compacted soil. So actually, unit weight, air void, unit weight density, we have to determine this first, no? So to determine that, how to do that one? First, remember that the moisture content, no? Or the dry unit weight is actually equal to the specific gravity times the unit weight of water over 1 plus E, di ba? But the zero air void for a given moisture content, the theoretical maximum dry density weight is obtained when no air is in the void spaces. That is when the degree of saturation equals 100%. Hence, the maximum dry density weight at a given moisture content with zero air voids can be obtained by substituting. So remember that to obtain the zero or unit weight zero air void, your S or degree of saturation should be 100%, diba? And remember that this formula, degree of saturation times void ratio is equal to the moisture content times the specific gravity of the soil. So that from here we have the specific gravity of the soil, unit weight of water, and this E, no, is if we set S or degree of saturation equal to 100%, this is equal to 1, diba? So that E is equal to moisture content times specific gravity. So, yung siya 1 plus this 1, diba? Then, we'll try to answer this. First, obtain this unit weight, zero air void is equal to 2.72 times the unit weight of the water is this given ko 9.81, no? Kilonewton. 9.81 kilonewton per cubic meter over 1 plus the moisture content 0.18 times 2.72. So that the zero air void is equal to, kailan na siya? $17.913. The truth is, I am not the one who made this kaning lecture note. I just borrowed this one from Sir Opiso, and some of the slides, no, is like this, no. We have to compute. So usahay makurutan ko question day siya. So anyway, maansira na siya. So that the unit weight, dry unit weight is equal to 0.9 times the unit weight zero air void. So 0.9 times 17.913, or this is equal to times 0.9, 16.122. This is equal to 16.122 kilonewton per. This is the answer. Another example is a laboratory test results of standard Proctor test given in the following table. Determine the maximum dry unit weight of compaction and the optimum moisture content. Alright, we have to draw this one, no? To obtain this one, draw the maximum dry density curve, no? Maximum dry density curve. So, we have there a table now. We have the volume of the mold, 1/30 feet cube, and the weight of the moist soil in pounds, in mold, no? In pounds. And different weight of moist soil. And the moisture content is given, no? Corresponding moisture content. So, the following table can be prepared. So, since not the volume given the weight, so we can obtain the moist unit weight of the soil by dividing the weight of the soil divided by the volume of the mold. And the moisture content is actually given, diba? Actually given in the table, so that we can determine the dry unit weight as this one is equal to, this one is actually equal to the moist unit weight divided by 1 plus the moisture content. So, subayon lang siya ninyo since given man siya. This is, we computed this one already and this is given. So, that is why we can obtain these values, no, of the dry unit weight. So, from here, we can draw the curve, no, moisture content versus the dry unit weight. For example, we have at moisture content 10, then the dry unit weight is 99, no? We have this one, no? This one and this one. This is for the x-axis and this is for the y-axis. So on and so forth until you can create this curve, the dry density curve. So your maximum from here, according to this graph, the maximum dry density is 106 pound per feet cube, and the moisture content, if you try to trace, is 14.4%. So the plot of the dry density versus the moisture content is shown in figure. From the plot, we see that the maximum dry density, dry unit weight is 106 pound per cubic feet, and that the optimum moisture content, corresponding optimum moisture content is 14.4%. So, we are required to, determine the maximum dry density, and then see the unit weight of compaction and the optimum moisture content. So, ingana lang, no? So, this is your final answers. So, we move on. Factors affecting the compaction. So, there are 5 factors affecting the compaction. Number 1 is the physical and chemical properties, the moisture content, method of compaction, amount of compactive effort, and thickness of layer or lift being compacted. Method of compaction. If it is standard Proctor or modified Proctor, the amount of compactive effort, no? So number of blows, no? Number of blows is per number, and thickness of layer or lift being compacted. So the effects of soil type. So the soil type is number 1, no, affecting the physical and chemical properties of the soil. So the soil type is grain size distribution or shape of soil grains, is specific gravity of soil solids, and the amount and type of clay minerals present. So these are the specific factors, no, for the effect of the chemical and physical properties of the soil. So ano siyang grain size distribution, shape of soil grains, specific gravity of soil solids, and the amount of type of clay minerals present. So these are the specific na further factors nga naka-affect sa compaction, no? So we have here the different kinds of soil, like here well-graded loamy sand, well-graded sandy loam, and its corresponding amount of sand, silt, clay, liquid limit, and the plasticity index. So if try to trace this one in the compaction curve, no, water content versus the dry density, ing ani ang iyahang behavior. So we have the behavior of number 1, kind well-graded loamy sand, so this one. And for number 2, well-graded loam, so this one. So galahi-lahi gid siya. So the effects of soil types, no, there is it is one of the factors na affecting the compaction. Another factors affecting the compaction is the compactive effort, no? Compactive or compaction effort. So as the compaction effort increase, no, the maximum dry density weight of compaction is also increased, and the optimum moisture content is decreased to some extent. Now, for example, this one, we have for number 1, we have 20 blows. So, dili na siya dapit, no? So, gamay ang ihang maximum dry density, which is at this konra. While ang 25 blows per layer, so gataas siya. So, mas dako ang iyang maximum dry density, but decrease the moisture content to some extent, no? So on and so forth. We have number 3, 30 blows, and number 4, 50 blows. Okay, meaning the degree of compaction is not directly proportional to the compaction effort. The effects of compaction effort, meaning this is the number of blows, no? Yes, this is the number of blows per layer. And effect of soil energy on compaction. This is continuation of compactive effort. So increasing compaction energy, that is lower moisture content and higher dry density. So higher energy meaning higher number of blows, no? Number of blows per layer. So munang lower moisture content since naraman siya diri dapit, and higher dry density, no? So in the lab, increasing compaction energy means increasing number of blows. In the field, increasing compaction energy, that is equal to the increasing number of passes or reducing the leaf depth, no? In the field, no? So kung pison, increasing the compaction energy meaning many times or daghan nga time imong balik-balikon o pison. While in the lab, if you use the standard Proctor test or the modified Proctor test, that is increasing the number of blows, no? The meaning of increasing compaction energy or compaction effort. And we have also the affecting, no, the compaction is the field and laboratory compaction. The method, no? It is difficult to choose a laboratory test that reproduces a given field compaction effort. So, galahi-lahi gid siya. So, actually, ang laboratory does not always represent the field, no? Then, the laboratory curves generally yield a somewhat lower optimum water content than the actual field optimum. Then, the majority of field compaction is controlled by dynamic laboratory, because majority of the field is controlled by dynamic laboratory test, or those like pison, no? Those equipment na dynamic. Like this one, no? This graph here, the 1, 2, 3, and 4 represent the laboratory compaction, while the 5 and 6 represent the field compaction. So, the laboratory compaction uses the standard or modified Proctor test, while the field compaction uses those pison, no, or the ruler, or those any equipment, no? So you can see nga The laboratory curves or laboratory compaction yield a lower optimum water than the field compaction. No? Higher. This one. No? This dash line represents the field compaction. So, lahi ang method, no? Also, method affects the compaction. Then, we move on to these properties and structure of compacted fine-grained soils. So, of course, we have to understand also how the soil particles behave if subject to compaction. So, for a given compactive effort and dry density, the soil tends to be more flocculated or random for compaction on the dry sand. So, in this part, on the dry sand, as compared on the wet sand, no? And for given molding water content, increasing the compactive effort tends to disperse or parallel or oriented the soil, especially on the dry side. So, yes, if you compare this one, so the dry density at this part, no, at this portion here, ga-random, no, ga-flocculate ang particles. Then, increasing the moisture content, ga-oriented na siya, parallel, no, dire, in wet portion, ga-orient na siya. And also, with high compactive effort, tends to disperse or parallel oriented ang soil compare with low compactive effort. Then, in terms of permeability, increasing the water content results in a decrease in the permeability on the dry side of the optimum moisture content and a slight increase in the permeability on the wet side of optimum. Yes, increasing the water content, decrease in the permeability and on the dry side, and the optimum moisture content and a slight increase in the permeability on the wet side. Like this one, no? This part here, this is permeability versus the water content. So, sa dry side, so increasing the water content, this part here, kapag gamay ang permeability, no? Kapag decrease. While after the optimum moisture content, so in the wet side, this part here, slightly ga-increase ang permeability, gamay. So, gamay na ga-slight pa. So, anyway, increasing the compactive effort reduces the permeability since it both increases the density. Yes. Increasing, thereby reducing the voids available for flow and increases the orientation of particles. So, this shows here that increasing the compactive effort reduces increasing the number of blows, mugamay ang permeability, tendency of the soil not to permit water, no? If increasing compactive effort. Since it both increases the dry density, thereby reducing the voids, no? Reducing the voids available for flow, and yes, it reduces the voids and increases the orientation of particles. So, the more oriented or parallel ang particles, no? Not dispersed na if increasing compactive effort. At low stresses, the sample compacted on the wet side is more compressible than the one compacted on the dry side. So on the wet side that is after the optimum moisture content that is in the wet side, at low stresses, more compressible siya because basa naman siya, mas basa siya than on the dry side of the optimum moisture content, no? And at high applied stresses, the sample on the dry side is more compressible, while this one, earlier at low stresses to siya. At this time, high applied stresses, the sample compacted on the dry side is more compressible than the sample compacted on the wet side. No, nagbali na po siya. In terms of swelling of compacted clays is greater for those compacted dry of optimum. They have a relatively greater deficiency of water and therefore have a greater tendency to absorb water and thus swell more. So, the explanation yan ng mas higher ang swelling potential because in this part of the dry portion of the soil is greater tendency nga mo-absorb siya tubig and thus mo-swell po siya dako mo ng higher swelling potential. Then this part here is higher shrinkage potential because mas daghang water diri dapit, mas daghang water diri dapit, so higher ang tendency nga mo dissolve or mo evaporate ang water, so mo na ang higher shrinkage potential. In terms of strength, samples kaolinite compacted dry of optimum tend to be more rigid and stronger than samples compacted wet of optimum. So, according to this notion, the kaolinite compacted at dry in this part, optimum tend to be more rigid. Now, in this part of the optimum, this one, this kaolinite. So, ang sa dry part, more rigid or stronger than compacted wet of optimum. And this one is properties continuation, strength continuation. We have also this term here, the California bearing ratio. This is the ratio between resistance required to penetrate a 3-inch square piston into the compacted specimen and resistance required to penetrate the same depth into standard sample of crushed stone. So the greater compactive effort produces greater California bearing ratio for dry optimum. However, the California bearing ratio is actually less for wet optimum for higher compaction energies. So for higher compactive effort, this one, greater this one, this one is the highest compactive effort among these samples. So according to this, the greater compactive effort produces greater California bearing ratio of optimum. Dry of optimum, this one is a dry of optimum. However, the California bearing ratio is less for the wet of optimum for higher compaction energies. For the summary of the in terms of with respect to compaction on the wet side, dry side and wet side of optimum, and with this criteria, the structure, permeability, compressibility, swelling, and strength, we have this in the dry side in terms of structure, more random, permeability, and the wet side, in terms of structure, more oriented or parallel. In terms of permeability, more permeable ang dry side. And compressibility, more compressible in high pressure range. And in the wet side, more compressible in low pressure range. In swelling, swell more because of higher water deficiency, and in the wet side, shrink more, and strength in the dry side is higher. So this is the continuation of the comparison on the compaction curve of the different criteria. So this can be found in Holtz and Kovacs. So I will try to post the book on the Google Classroom, including this video. And engineering properties for the notes, engineers must consider not only the behavior of the soil as compacted, but the behavior of the soil in the completed structure, especially at the time when the stability or deformation of the structure is most critical. For example, consider an element of compacted soil in a dam core. As the height of dam increases, the total stresses of the soil element increase. So when a dam is performing its intended function of retaining water, the percent saturation of the compacted soil element is increased by the permitting water. Thus, the engineer designing the earth dam must consider not only the strength and compressibility of the soil element as compacted, but also its properties after it has been subjected to increased total stresses and saturated by permitting water. No? So, I hope this is standard understandable. Is there a word like understandable? I hope this is like self-explanatory, no? This one. So we have, okay, now we move on to the field compaction equipment and procedures. So in the field soil compaction, because of the differences between the laboratory and the field compaction methods, the maximum dry density in the field may reach 90% to 95%. No? So compare this. This is in the laboratory and this is in the field. So we have here a figure of the optimum moisture content and versus the dry density. So this is in the field, no? May reach 90 to 95%. So we have different soil compaction in the field. So we have different equipment. Now we have the rammers, the vibratory plates, smooth rulers, rubber tire, ship foot ruler, and dynamic compaction. So we'll not discuss this one by one, but you can read this one by yourself na lang, no? And understand. We have this smooth wheel ruler, pneumatic or rubber tired ruler, ship's foot ruler. So these are the compaction equipment in the field. The tamping foot ruler, the mesh or grid pattern ruler, vibrating drum or smooth wheel ruler. And this is the summary now of the different rulers and its compactive efforts. Like for high speed damping foot, so hangtod nga. Then for the field compaction control and specifications, the control parameters, dry density and water content correlate well with the engineering properties, and thus they are convenient construction control parameters. Since the objective of the compaction is to stabilize soils and improve their engineering behavior, it is important to keep in mind the desired engineering properties of the field, not just its dry density and water content. This point is often lost in earthwork construction control. Design construct procedures. Laboratory tests are conducted on samples of the proposed borrow materials to define the properties required for design. After the earth structure is designed, the compaction specifications are written. Field compaction control tests are specified, and the results of this become the standard for controlling the project. So yes, we have this specification now in the field. We have the end product specifications. This specification is used for most highways and building foundation as long as the contractor is able to obtain the specified relative compaction. How he obtains it doesn't matter, or does the equipment he uses. Care the results only. While the method is specifications, the type and weight of ruler, the number of passes of that ruler, as well as the lift thickness are specified. A maximum allowable size of material may also be specified. It is typically used for large compaction project.